In this lesson, we'll be discussing Prometheus histograms. Now, if you're wondering why you might want to use a histogram, let's look at an example from the Google Site Reliability Engineering book, which you can also read online for free. One of the chapters is about the notion of service level objectives, in which they provide a methodology for measuring the performance of a particular service and how you know whether that service is healthy or not. So Google recommends coming up with three different measurements: a service level indicator, which is how you're measuring something; a service level objective, which is what are the boundaries for how you decide whether that indicator is healthy; and optionally, a service level agreement, which is basically what you should do if you don't meet your service level objective. And so if you get down into reading what they recommend here, it says most services consider request latency, or how long it takes to return a response to a request, as a key SLI. So when we're measuring latencies, like how long it takes for a certain endpoint to respond, if you're measuring individual timings kind of at the log level and you're just aggregating logs, you can be dealing with just a huge amount of data. It can get very overwhelming. So one of the things that Prometheus allows you to do with histograms is you can measure these request latencies right at the server side where the requests are being served, and then you can just expose a summarized view of those latencies in the form of a Prometheus histogram, which shows you an aggregated view of the distribution of those values. So you can see if you have a distribution where most of your values are clumped around a certain value, and maybe you have some outliers that are much higher or much lower. Also with histograms, you can satisfy another recommendation of the Site Reliability Engineering book, where you can think of your distribution in terms of percentiles. And this allows you to say things like, okay, 95% of my request latencies are being served within 200 milliseconds, or 85% of my request latencies are being served in under 100 milliseconds. And the reason that you might want to do that, as they describe here, is, okay, you might want to say that the 99th percentile kind of shows you sort of a worst case value, which is discarding everything except the most extreme outliers. And the 50th percentile, which is another way of expressing the median, is showing you the typical case. So this allows you as a developer working on a service to kind of set expectations for how your service should perform by setting an appropriate SLO and then providing the tooling so that you can actually measure it and get alerted if it goes outside of those boundaries. The concept of a histogram type metric in Prometheus is very powerful, but sometimes it can be a little hard to wrap your head around. So let's start with a basic example. So histograms revolve around the concept of buckets. So if we think of having three buckets that are actual physical buckets like this that we can drop something into, and we give them a name like, let's say, 0 to 5, 5 to 10, 10 to 15. And let's say we have a bunch of numbers like 3, 4, 7, 9, 11. And we want to put these numbers into their proper buckets. So pretty straightforward. 3 goes into this bucket because it's between 0 and 5. 4 also goes into that bucket. 7 goes into the middle bucket. 9 also goes into the middle bucket, and 11 goes into the middle bucket. Pretty straightforward. Now, let's do another example here where, now let's talk about how Prometheus does bucketing a little bit differently. When you create a Prometheus histogram, you are defining those very same buckets, except instead of being discrete buckets, where one number only goes into one bucket, Prometheus uses what's called a cumulative histogram. And let's see what that means. So let's create another bucket, and we'll give it a value of 5, and we'll talk about what this means in a second here. Another bucket with a value of 10, and another bucket with a value of 15. Now, when you actually define these bucket boundaries in Prometheus, instead of just being a range like 0 to 5, 5 to 10, 10 to 15, Prometheus actually puts this prefix LE in front of each bucket. And what this actually means is less than or equal to. So let's again take a few numbers here. Let's say 3, 4, 7, 9, 11. So when we do less than or equal to type buckets, things work a little bit differently. So let's take the number 3. Is 3 less than or equal to 5? Yes, it is. Now, is 3 also less than or equal to 10? Absolutely. So 3 actually goes in this bucket too. And because 3 is less than or equal to 15, it also goes into the less than or equal to 15 bucket. Now, behind the scenes, Prometheus is storing all of these bucket observations as counters. So when we drop the 3 into the 5 bucket, that counter gets incremented to 1, the 10 gets incremented to 1, 15 gets incremented to 1. Now, when we observe a value of 4, it's less than or equal to 5, so we increment the 5 bucket. It's less than or equal to 10, so we increment the 10 bucket. Less than or equal to 15, so we increment the 15 bucket. When we observe 7, now in this case, it's not less than or equal to 5, so we don't increment that bucket, but we do increment the 10 bucket because 7 is less than or equal to 10, so that bucket goes to 3. The 15 bucket goes to 3 as well. Moving on to 9. 9 is less than or equal to 10, so we increment the 10 bucket. Less than or equal to 15, we increment the 15 bucket. And finally, 11 is not less than or equal to 5 nor 10, but it is less than or equal to 15, so we increment the 15 bucket to a value of 5. So we wind up with some final values of 2, 4, and 5 for the counters for these 3 buckets, respectively. Now let's change this to a little bit more of a concrete real-world example. So I've got a Node.js application that does one simple thing. When you call its API, it returns a random dictionary word. And I have instrumented my Node app using this package called Express Prom Bundle because my Node.js server is an Express server. And what this package does is it automatically instruments all of the endpoints in that application with Prometheus Histogram so that we can measure the response timings for every endpoint that we're hitting. So if we look in my editor here, I've added this initialization step here, which calls that prom bundle package. Here, what's going on is I have defined my bucket boundaries as 50 milliseconds, 100 milliseconds, 150, 200, 250, 300, 350, 400, 450, and 500 milliseconds. Now, in addition to what you see here, Prometheus will automatically create one additional bucket called plus infinity to represent any observed values that are greater than this last bucket boundary here. So we won't get too much into the code here. Basically what's going on is every time we call the word API, we are returning a random word from a dictionary object that I have here in JSON format. You can see I've just got every word in the unabridged dictionary. And I have also added some additional logic here, which is going to introduce some artificial random latency. into these responses, just because this is such a simple app that if I didn't do this, everything would just get returned instantly. So I'm basically doing some math to introduce random latency that's going to fit into a bell curve distribution. So most of my latencies are going to be clumped around the middle of this distribution, which is going to be around 250, 300 milliseconds, and then fewer values are going to be observed kind of around the fringes of that. So let's just see this in action here. So I'm going to curl localhost on port 8081 where my Express app is listening, call the word API, and I get a word. And then if I look at my app behind the scenes here, I can see that I have gotten that it's waited 525 milliseconds to return that word. So now that we've observed one value, if I go into Prometheus, the Express Prom bundle automatically generates a metric that's called HTTP request duration seconds bucket. And this can optionally break it down with labels so you can have separate metrics for each method. So in this case, /word is the method that I'm looking at. So I'm going to execute this, and I can see that I've got one single counter bucket that's been incremented for the plus infinity. And the reason for that is because you remember my biggest bucket boundary was 500 milliseconds, and I actually observed a value greater than 500 milliseconds. So let's observe some more values and see what happens. So next, I've got a word aluminotype. That value was 495 milliseconds. So if I run this query again, you'll see that my plus infinity bucket has also incremented again, and that's because 495 milliseconds is less than or equal to infinity. But I've also incremented this bucket here, less than or equal to 0.5. Remember, this value is in seconds, so 0.5 seconds is 500 milliseconds. So let's just do another value here. Let's see if I get something more towards the middle. Okay, that was 448. So again, I'm seeing that same bucket is incremented. Try to see if a smaller one comes up here. Okay, here's a smaller one, 209 milliseconds. So now if I execute this Prometheus query, you can see that several of my buckets have incremented for less than or equal to 250, 300 milliseconds, 350, 400. So you can start to get a feel for how this is going to work. Now, to make this a little bit more interesting and to make it so I don't have to sit here and run a bunch of curl commands individually, I'm going to make use of a really cool Node utility called load test, which basically allows us to deliver a constant stream of HTTP requests at a specific rate to an API of our choosing. So I'm going to go ahead and run this command, load test. Now these parameters here, -c means concurrency, so this means I'm basically going to have 10 workers that are all going to be running at the same time. RPS 100 means I'm telling the tool to try its best to deliver a constant rate of requests of 100 requests per second, and I'm going to curl, or I'm going to hit the same API endpoint here. So this is going to go off. It's going to, every now and then, it's going to log some messages to my console telling me the mean latency and requests per second and how many requests it's sent altogether. If I go back to my application console here, you can see I'm now getting a nice big barrage of requests here. I'll try to scroll down to the bottom here so I can see them all coming through. Okay, there we go. So now if I go back to Prometheus, we should start to see something a lot more interesting here. Yeah, so now every time I execute this query, Prometheus is actually scraping this this endpoint every 5 seconds. So yeah, I can see that that I'm starting to get an interesting distribution here. You'll see something super interesting is that towards the bottom, the lower buckets here, 50 milliseconds and 100 milliseconds, I've barely got any observed values for under 100 milliseconds, and I actually have 0 for under 50 milliseconds. So that tells me that that none of my responses have been lower than 50 milliseconds, and only a small handful have been under 100 milliseconds. So you might be thinking, okay, this is interesting to see all these values here, you know, represented as numbers, but what if I actually want to represent them visually and graph them? I'm going to go into Grafana and create a new dashboard, and just to see kind of what these values look like as we graph them, I'm going to create a simple graph type here. And I'm going to go ahead and put in HTTP request duration seconds bucket and give it a label filter of path equals word. Now, what's going on here? So we're seeing this kind of dark side of the moon prism effect here. This is because, as we talked about behind the scenes, change this to every 5 minutes to last 5 minutes so we can see this a little better. Because these are counters and these are only ever increasing, this is what the raw data actually looks like. And we can see that certain counter values are increasing far faster than the other ones. So towards the bottom here, we've got the less than or equal to 50 milliseconds, which still has a value of 0, and 0.1 or 100 milliseconds, which is equal to 34, 57. Okay, you can see right here towards the end, we've finally gotten one observed value for less than or equal to 50 milliseconds. But this isn't really super interesting. If you're actually monitoring, you know, a real production API, this isn't really super useful to see the data visualized this way. In recent versions of Grafana, they have actually created a new graph type called Heatmap, which is specifically designed for visualizing histograms. So let's go ahead and create a histogram, or create a heat map. Let's edit this here, and we'll give it the same value, HTTP request duration seconds bucket, path equals word. By default, this is showing us sort of the same cumulative counter effect here. So we're seeing all of these blocks sort of going up in value here. And the reason for that is because Grafana is a very generic tool that is designed to work with a lot of different backing data sources, not just Prometheus. So we have to tell Grafana a little bit about how Prometheus is sending this data. So the first thing we have to do is we have to change our axis tab here, and we have to go into this data format. And this tooltip gives us a little clue here about what's going on. So by default, the format is time series, but what we actually want is this second value time series bucket, and that says use histogram data returned from data source. Each series represents bucket, which upper lower bound is a series label. So remember that Prometheus automatically created all of these labels for us based on the time series boundary, and those labels themselves, the LE.5, LE.250, represent the time series boundaries for those buckets. So if we change this to time series buckets, now we're starting to see this look a little bit differently here. Something that we also have to do, because you see on the left side here, this left axis is like full of the entire metric name and all of the metric labels. What we want to tell Prometheus is that the y-axis which should show us the bucket boundaries, we need to tell it how to format that label. So to do that, we use a double curly brace, and we say LE, which is the label called less than or equal to, and then close double curly braces. And now we'll see that our y-axis is showing us these bucket boundaries based on our labels. Now again, remember this is values in seconds, so 0.50 means 500 milliseconds. If we want this to be a little bit more user-friendly, we can actually go into this axis tab here and change our unit from short, which is just showing us a simple number. We can change this to time seconds. And now we can see that it's actually showing us this formatted in millisecond form. So now that this has been running for a while, we can change this to show last 15 minutes. And as this load test is ramping up, we can start to see that we're seeing kind of a clustering effect here towards the middle. So a heat map is going to show us kind of 3 dimensions in one graph, which is pretty cool. So on the x-axis here, we're looking at the time when these values were observed. The y-axis is showing us which buckets these values were dropped into. Now remember that these values are cumulative, right? So so we're looking at counters that are always going up. And what that means for Grafana is that when we look at these values here, if we hover over any one particular tooltip here, it's showing us the density of how many values were observed for that particular block. And we'll see that just like with the counter, these are always going up. So if I'm looking at my 300 to 350 milliseconds bucket, you can see that here around 748, it was at like 2,700 observed values, but this is only ever going up. So this still isn't really showing us the true nature of what's going on just for this interval of time. We're still looking at cumulative counters. So what we have to do is, instead of just graphing this metric just on its own, we actually have to wrap this in a function called increase. And we have to give it a value to tell Prometheus, instead of returning the cumulative value of that counter, only return us the value of how much that counter has increased over a certain interval of time. So let's say 1 minute. So what we're seeing here is now for each particular square, you can see that instead of these squares always going up, that these are showing us just how much this particular bucket has increased looking back at the previous minute. And remember that I mentioned that our app was modified to return some random latencies distributed along a bell curve. I also introduced some logic that kind of adjusts the jitter factor so that the center of the bell curve is actually going to change to be slightly higher and slightly lower. So we can see this as the sort of hottest point here, like the white hot point of this graph is sort of oscillating up and down. So the white area represents the most frequently observed values. You can see that this shows us like in 1 minute we got 1,000 values that were between 350 and 400 milliseconds. If I look down, more towards 100 to 150 here, we only had 65. You'll also notice that it's showing us 65.538. This is because behind the scenes, Prometheus is kind of doing some averaging. It's taking aggregate data and it's returning an estimate. So this isn't going to be the exact number of values, but it's going to be a very close approximation. And that's just because it's a design philosophy of Prometheus to be fast rather than to be 100% statistically accurate. Now, if somebody is looking at this graph for the first time, they might wonder like, okay, well, what do the colors mean? So something we can do to make this a little bit more obvious is we can go to our display tab here and we can click this button that says show legend. And now what we get here is this nice little color-coded legend here that shows us if we're at the deepest, darkest red, that's 0. As we start to move towards the oranges, that's like 500 values observed. And then as we start to get towards the yellow and white, then we're starting to get towards over 1,000. And the cool thing is that this color coding and the values associated with it will automatically adjust. So if I drag my graph to just look at this slice here, you can see that the numbers have actually changed. So let's go back again to look at the last 15 minutes here. Another cool thing we can do is we can change our color scheme. If you don't want to see this kind of oranges and reds here, one that I like to use is spectral, which shows us kind of more of a graph, from cooler, representing fewer values, to hotter, red colors representing more frequent values. I find this one to be slightly more intuitive. You can also choose ones that are red, yellow, green, or there's one that is just grays, if that's more your thing. So there's lots of options here. Something else you can do just to kind of change the look and feel of this graph, you can adjust the spacing, and this is actually adjusting the sort of the black border around each square. You could actually, I think this is a value in pixels, so you could make this, I don't know why you would want to increase that value. Something that I like to do sometimes is give it a value of 0, and that just gets rid of the black borders altogether. You can choose aesthetically what you like to do. You can also give it sort of a rounded effect. If you want to make each pixel or each square slightly rounded, you could do that. And another cool thing you can do, if you'll notice the tooltip here, when I hover over, right now it's just showing me the count of observed values. If you click this histogram button, what this will actually do is change your tooltip to show you the distribution just at that value. So here what I'm seeing is sort of a visual representation of just this vertical slice here in time. And I can see that I've got more of a clustering towards sort of the top third of my of my buckets here. But as I slide over, you can see that my midpoint has shifted, so my bell curve is more exactly at the center. And again, let's look back. If I slide this over, my bell curve is more towards the right. Now it's more towards the center. And then if I slide over to this side, it's even slightly left of center. So this can be something that's interesting, especially if you're looking at a histogram with a large volume of data, or a heat map with a large volume of data. Sometimes having this histogram representation where you can slide this around can be helpful as well.